Good evening, everyone. I welcome you to the week 7 live session of this many body methods in quantum chemistry. So we have been so far taken six live session, and this is the seventh one. And in the sixth live session, we have done some of the assignment problems. Now, because of the time constant, we couldn't finish some of the problems, which we are going to do in this live session. And uh, in the very beginning, I want to tell you that because I have fever, so due to my feeble voice or any inconvenience, I'm really sorry for that. So please bear with me. And so first we'll begin with I will try to solve this question. Consider a system of three non-interacting identical spin half particles that are in the same spin half-half, right? So, so carefully read this question first. So it says that consider a system that is consists of three non-interacting identical spin-half particles, and it is
Actually, we
given
had
that
our mid-semester exams, so we could not
yes,
join last classes.
yeah, okay,
Can
yes, yeah, go ahead.
you explain this problem from the starting?
Yes, this problem, right? Okay, so this is a very separate problem. You don't need to have the previous thing, I guess. So the previous problems was also different. So this is a new problem that you can solve from the beginning itself. And if you have any doubt, you can go through the recording of the lectures. I think that would be fine. Okay, so let's read the questions once. So it says that consider a system of three non-interacting identical. So the first thing is that it says that it's a non-interacting particle. So yes, so it says that it's a non-interacting particle. Now the state of this spin state is half-half. That means it's a alpha spin. Right, so every particle, the spin-half particles, are in the alpha spin and confined to move in a one-dimensional infinite potential of well, which is a length of L, where Vx is 0 inside the box and Vx is infinite. So it's basically your particle in a one-dimensional problem. So the question asks to determine the ground state energy and the wave function in terms of Slater determinant. Now the given informations are inside the box, the single particle single particle energy. So you very well know this equation, En is equal to m square h square by 8ml square, and this is your one particle wave function. So the thing is, from solving this one dimensional particle in a box, you have these three states, right? Where your En is m square h square 8ml square, and your n goes from 1 to dot up to infinite. So this is your n is equal to 1 state, n is equal to 2 state, and n is equal to 3 state. Now you have to fill the half spin half particles in a very clever way. So it is given that the same spin state, right? So if you fill one electron here, because of the Pauli's exclusion principle, you cannot put another electron here. And it is said that every spin of particles have the same spin, that is your alpha spin. So you have to put another electron here and another electron here. When you have this clear idea, now everything is very simple. So the first thing is that as it is a non-interacting system, so that means its Hamiltonian is basically H1 plus H2 plus H3. So you can write the energy, the total energy, as a summation of the individual energy, E1 plus E2 plus E3, which is, so you can take common h square by 8ml square. Now you are left with 1 square, 2 square, and 3 square, which will give you h square by 8ml square square 1, 4, and 9, which is 14. So 14 h square 8ml square. So this is your total energy. Now it is said that as it's a spin half particle, so you can write the total wave function in terms of the Slater determinant. So you can now define the phi 1 as, so now you have three state that is occupied, n is equal to 1, n is equal to 2, n is equal to 3, right? So phi 1 you can write, so this is basically root over of 2 by L sine n uh, 1 by L. So the three spin orbitals are pi 1 root over of 2L sine 1 pi L times your the alpha spin, and phi 2 root over of 2 by L sine 2 pi L by L times alpha omega, because they all have the same spin, and phi 3 root over of 2 by L sine 3 by L alpha omega. Now you can easily write the total Slater determinant or the wave function of the system, which is 1 by root over of 3 factorial, because you have 3 electrons. Now you write phi 1, phi 1, phi 1, phi 2, phi 2, phi 3, phi. Now just fill the electrons. 1, Mm. Now, as this is a non-interacting system, the wave function, that is the anti-symmetrized wave function 1, 2, 3 you got, that is actually the exact solution of this problem. And the total energy that you got, that is 14 h square by 8 ml square, that is also the exact energy of this state. Any doubts so far?
No. Did we prove how that 1 by root 3 factorial?
Yes, I think you have asked me the question, and that time I told you that to make it normalize, so psi star psi uh, has to come out to be 1. So if you just try with a uh, two two particle system and three particle
Oh yeah.
system, you can see from there you can get this factorial. This actually makes this wave function normalized. So let's do this question. First of all, why I'm doing all this, because so this is a very, it's a mathematical question. So this is asked in the IIT Bombay's uh, advanced quantum chemistry questions assignment. So I thought it will be very good to solve this question, because these ideas will be used in the advanced level, whether your couple cluster theory and all the other stuff. So this is called the Baker-Campbell Hausdorff expansion. So later, this after this proof, um, we'll tell that how you can get that Baker Campbell Hausdorff expansion that is very often used in the couple cluster theory. So that's why we'll go very step by step. We'll solve this question first. So these two questions, which may take some time. Then in the later part, we'll discuss the perturbation theory slides, again from Marshall's. One slide there. There are some few slides. So let's first solve this question. So it says that let A and B be linear operators such that all required commutators exist and formal power series expansion are valid. Define an operator Z such that exponential A exponential times exponential B is equal to exponential Z. Now we have to show that if A and B commutes with each other, that is the commutator of A and B is 0, then we can show that Z is equal to A plus B. Would you like to try this question?
Uh,
To take some time, maybe 5 minutes, then we'll solve this question.
What does required commutators exist mean?
Your voice is echoing.
Like, what does the term like required commutators exist means here?
So it actually means that A, B, and B, all the commutators exist. So as such, I don't. see any problem that all required commutators exist. Oh yeah, so you will see eventually that you can take any linear, so not linear combination, but I will say nested commutators that will appear actually. You can see from here. So this is the normal commutator, but if you go here, so this is a nested commutator. So these kind of commutators actually exist. So that's what it
Okay.
says. So we'll come to this, like how they are coming.
I'm trying it now.
Yeah.
Is it just like the taking the log and it's done
So you have taken the log.
of the given expression definition of Z?
So you have taken log, like natural log, right?
Yeah, yeah.
Okay, let's. So you have taken this to the A to the B, that's it. And so ln AB is ln A plus B. So ln.
But I don't understand like why is the commutator required to be zero
Yes, yes, yes.
to
So
prove this?
you'll come to see that, but let me. So now if you take that ln C, I am not sure that whether it's an operator. It's an operator. Um, can we just do ln E? Uh,
Like, if it's acts on a function, then maybe like A of F.
and actually, this is also very simple. Like if you if you just take this as e to the power a plus b from the you know
Mhm.
uh,
Oh, okay, okay, yeah.
then e to the power z. But actually, this is not how it is solved. So I have to actually look. I think this is not allowed unless or until this commutator. So I haven't looked in that way. That was also very simple. But I from the beginning I have started thinking in a complex way. Oh, but just let me.
I think this is the correct because log it's not a constant. So
No, I'll show you that if they do not commute, you actually cannot write this from here to here. So let me prove first, then maybe we can comment
okay,
that whether it's possible or not. But again,
okay.
I'm not sure, but I have to have a look. So let's see the formal way it is done. So the thing is, the left hand side, your left hand side is exponential A, exponential B. Now, any exponential, for example, e to the power a, you can write it as 1 plus a, then a square by 2 factorial, a cube by 3 factorial, and so on, like so on. So you can just simply write summation of n is equal to 0 to infinity a to the power n divided by n factorial. So if your n is 0, then it's 1. And similarly, for b, you can write m is equal to 0 to infinity b to the power m factorial. Or you can combine this, n is equal to 0, m is equal to 0, infinity, infinity, and now you have a to the power n, b to the power n factorial, n factorial. Now, so you can see that you will have like different cross products. So b plus b square by 2 factorial, b cube by 3 factorial, and so on. So you can see that this one, so if you take a product of this e to the power a and e to the power b, you will have a various terms like this one will multiply with 1 to give you 1, then b square,
Hmm.
these terms, and with a
Hmm.
also you will get ab. So the total power, so if you take the total power of A and B, so when these A and B are multiplied together, so total power is 1 plus 1, so that is 2. Now, then this A and B square, that is cube. So in the similar way, this A square and B, there will be total power of cube. So let me write the expression then. So instead of this, we can write this as, so I'll explain. K to the, we can write k is equal to 0 to infinity and n is equal to 0 to k and a to the power n, b to the power k minus n factorial, n k minus n factorial. Now, so where k is the total power, that is n plus n. So I'm defining a new index, that is k is equal to n plus m. So from where you can write m is equal to n minus k. So you can see in this b power, I have replaced this m with k minus n and this m with k minus n here.
Hmm.
And so the total power, so this n goes from 0 to infinity, m goes from 0 to infinity. So the total power, that is k, that is going to 0 to infinity. Now I am reducing this summation n is equal to 0 to k. So actually I'm grouping all the terms. So if you see that a to the power n and b to the power k minus n, if you sum the total power, it is actually k. So you will have different powers. So you can have 0, 1, 2, 3. This is the k, the power of k. So you can actually, you are taking this all the terms, but you are grouping the terms in terms of the total power of a and b. So this, the way we did it, that it is actually called a Cauchy product. So if you just simply do some multiplication from here, right?
Like total power or the highest power of the product.
So
Yeah.
the total power means you, so see, your k, when your k is 0 and n is 0, right? So in that case, what you have? You have 1. So this you are getting. Now, so let's say when k is equal to 1, right? So when k is equal to 1, so here your k is getting settled 1 here. So now your n will be 0 and 1, right? 0 to 1. So now you will have a to the
0
power
to
a to the power 0 and b to the power k minus 1. So this is actually your b. So that, and you will have another term where n will be 1. So n will be 1 and your b will be, your k is 1. So 1 minus 1 is 0. So a. So see, when your a multiplies with this 1 and this b multiplies with this 1, you will get these two product. So are you
So
getting?
can you repeat this once? Like,
Okay, so let's say, what do I mean by total power? So when your k is 0,
hmm,
okay, when your k is 0, then your n
hmm,
is 0,
hmm.
right? So you have the term that is left after the multiplication, that is 1. That is very simple.
Yeah,
Okay,
yeah, yeah,
now,
yeah.
so let's say here your k is 0. So n
Hmm,
goes from 0 to k. So your
hmm,
k is 0. So your n is actually 0. So a to the power 0 and b to the power 0 and divided by 1. So that is actually 1.
hmm,
Right. So you got 1. So which you were supposed to get from here also after the multiplication. 1 1, that will give you 1. So you got one term here, that is 1.
hmm,
Now your k can be 1.
hmm.
Now your k can be 1. So now your k is set here 1. So now what is the value n can take? N can take 0 and 1, two value. See this summation? Your n will go from 0 to k, that is 1.
Hmm.
Right. So then what are the term you have? So let's say your a to the power n, so a to the power 0 and b to the power k is 1 and n is 0. So what you have? B. And
Yeah.
again, you can have n is equal to 1. So you have a1 and b to the power your 1 minus 1. So a. So you have a plus b. So you are actually grouping the term in terms of. So let's do another example. I think it will be more clear. So if now your k is 2,
Hmm,
so total power has to be 2. So even
hmm.
without doing it, I can say it will be a square. Like, then the terms will come, the 2 factorial either. I'm not writing that. It will be b square, it will be ab and ba.
Hmm.
Right? So these
Okay,
four,
so that's why.
this way I'm writing all the terms.
Hmm,
Okay.
hmm.
Now, please look carefully that here A and B are an operator and I don't know whether they commute or not. So I
Hmm.
have written in terms of AB and BA. Okay.
Okay.
So this is called Cauchy's product.
Hmm,
Now let's divide and multiply with k factorial. So what I am doing is k is equal to 0 to infinity 1 by k factorial. I'm dividing with k factorial and then n is equal to 0. K, you have k factorial n factorial k minus n factorial, and you are left with a to the power n b to the power k minus n. Okay, so your left hand side becomes
hmm.
summation over k is equal to 0 to infinity, summation over k is equal to 0 to infinity, and 1 by k factorial summation over n is equal to 0 n is equal to 0. So I can write this term. This is basically your NCK.
KCN in
Oh,
CK.
yeah, KCN. So that is your KCN. And you have a to the power n, b to the power k minus n. A to the power n, b to the power k minus n. Okay. Now, if you remember
Okay.
one thing,
Is 1 plus AB whole to the power K.
yeah, so this is the formula actually. So for
Mm,
any, it's a formula. This is actually your binomial coefficient. So
mm,
x to the power a plus n, the formula is nck x to the power k and a to the power n minus k, like this. And your k goes from 0 to n. I think this is visible. Sorry for the handwriting. So this is basically k is equal to 0, infinity, 1 by k factorial. And these binomial theorems only holds if if x and a are number, then that doesn't matter. But if this x and a are operator, and they have to follow this condition that this is 0. Otherwise, so actually when you write x a square,
mhm,
so now you have x square plus a square plus 2xa, right? This you can only
mm,
write when you have the commutator relation. Otherwise, if they don't commute, now you have this xa and ax. Right? Then you cannot write this as the binomial formula. So up to this is fine. Up
yeah.
to this is fine. But when you are going from this equation to to write this at a plus b to the power k, here you are putting this constant that ab actually commutes. Okay, so that is what actually required here. So now this is very simple. You can see that this is nothing but the formula of your e to the power a plus b. So
Mm,
this one. So, and this is e to the power z, and this says your z is equal to a plus b. And now here actually it was required that your AB has to be A and B has to commute with each other. But if you just do
mm.
e to the power,
Basically, we are proving
yes,
the
proving the,
operators also uh, follow the exponential addition rule.
yeah, actually you can
If they
write,
commute.
yes, so you can write this binomial expression only if this is like A and B commutes with each other. So it was very straightforward. So while writing this e to the power A and e to the power B, like I have to see like when you write this e to the power A plus B, actually you um, actually you consider, I think, that A and B commits each other. So I haven't done the formal proof that this you can only write. So then it was a two-line proof, right? If you can write e to the power a, e to the power b is equal to e to the power a plus b, just like the way we do with the numbers. But I think there are some more into it. I have to think about it, but this is the actual way that it is done. Mm, so uh, do, do square. Yeah, actually, I have to have a look. I don't know the immediate answer to this. But yes, this was the proof. Now let's do this. So it says that by expanding both sides, so we had e to the power a, e to the power b is equal to e to the power z. By expanding both sides in power series up to second order in a and b, and assuming that z is equal to a plus b plus c2. So now here what you are doing is that you are assuming that your z contains up to the second order term only. Now you have to prove that this C2, the second order term, is nothing but the half commutator A and B. So let me prove this one. Uh,
So assuming like a plus b till a plus b square only.
Sorry,
So we have to assume like in the power series there is only till a plus b square by 2 factorial. Is that
the second order terms means only AB, BA, or A square, B square. Only the second order term would be there, not like A cube or AB square or B square A. This kind of terms won't be there. You have to only contact up to second order term. So here I am not assuming that A and B commutes. If A and B commutes, then your Z pretty straightforward that we have proved that Z is equal to A plus B. Now,
so
if
the C2 is just second order term.
C2 will prove that it actually looks like this. So, so here we are not assuming. So from this example, you can see if your A and B commute, then C2 is what? 0, right? Then Z
Hmm.
is equal to A plus B. So in the previous proof, we did that if A and B commutes, then it's fine. But see, when A and B doesn't commute, then you cannot write. So, so you cannot actually write that Z is equal to A plus B. Okay, so let's write up to the left hand side. So it will be 1 plus A plus A square by 2 factorial. And I'm not taking the other terms because that will be above second order. So now you have 1 plus B square by 2 factorial. Now let's collect the up to the second order term. So now here will be 1 plus A plus A plus A square by 2 factorial. Then B plus AB. So 1 A square by 2 B AB, and AB square by 2 factorial we are not taking because that is third order in term. And now you have A square by 2 factorial, and whatever the terms are there, that is order of 3. 1 plus A, we have 1 plus A plus B plus AB, A square by 2 factorial. Oh, that was B, sorry. It will be square by 2 factorial and order of 3. Yes. So this is the left hand side. And what about the right hand side? Your right hand side is e to the power z. And so this is your 1 plus z plus z square by 2 factorial. Now it is given that your z is a plus b plus c2. Right. So here it will be 1 plus in place of Z you can put A plus B plus C2 by 1 by 2 factorial A plus B plus C2 whole square. Now next page. So now you can write this as 1 plus A plus B plus C2, A plus B plus C2, 1 by half. So when you take the square, so up to second order you can see you can have only the terms like A square, B square, and there will be cross product like so when C2 times B, so C2 is already second order. So here it is written that C2 contains only second order term. So C2 times B, that will be third order, that we are not going to take. C2 times A, third order. C2 square is fourth order. So we are not going to take. So only you can see AB and BA, these two terms will be coming out. So we will have AB plus BA. and yes, there will be A square and B square term also.
We are expanding the exponential till second order, and then even
Hmm.
after multiplication, we are
Yes, because
ignoring the.
yes, because they are the higher order terms that we are not taking. So we are maintaining that we will only take up to the, so actually what we are doing here in the Cauchy product, so we are only taking k is equal to 2. So from here actually you can write the terms very quickly also. So in the last part, when we'll do this problem, we won't solve fully, but I'll show you how to solve this. So in that we'll use that Cauchy product approach. So this is we have b square by 2, right? I think we have written 1 plus a plus b plus c2 plus 1 by 2 factorial a square b square. Yes. Okay. So now we have to just do left hand side plus right hand side. So this 1 plus ab plus a square by 2 factorial, these terms will get cancelled. This one, and this will get cancelled. So right hand side you have C2 plus half AB plus half BA. So see here, if A and B commutes, we could have just write it as AB something like that, but we are not considering whether they commute or not. We'll write in terms of commutator. So here C2 and here only the AB term will survive. Yes, because this A, this one, these and these, and we are not taking any third order terms. Yes, so this will survive. So C2 we can write as AB minus half AB minus half BA, which is half AB minus BA, and C2 is A commutator B. So it is proved. Any doubts so far?
No.
So similar approach we'll do. Just 1 second. So you had your mid-sem exams, you told, right?
Yeah.
Okay. So then are you seeing all the lectures up to perturbation theory?
Yeah. Till week 7, I'm about to complete.
Mhm.
Perturbation theory, yeah.
Okay.
I have one lecture is left, the last one.
Okay. So in the perturbation
I
theory
just,
again, yes.
yeah, you were telling me.
Yes, so today also most of the stuff that I'll discuss that is already been covered, but there are some plots that will be interesting, and maybe if I get some time, I can just quickly show how to run a MP2 in Orca. And do you know how
On
to use
Orca.
Orca?
The Orca I have not yet like used.
Okay, I'll just show a simple example. Maybe do I have? Uh, yes, so I'll show you if I have time. It's
In the last two lectures, what did you cover?
uh in the last two lectures, yes, I have covered the basis set slides given by David Shedil and the electronic correlation from the same professor, and I have solved some assignment problems, very few, and I have shown you how to uh, extract the basis set from the basis set exchange website. And there I have shown you that like I think it is already been discussed, but in the website that you can see how do you when you add diffuse function, what is polarization function, and in the basis sets that I have shown already. So you can just quickly go through that. Uh, yeah, so let's do this one. So now it is told, so you can try this at home. So I'll just
Yeah.
briefly sketch the problem. So now it is like they have asked you to consider up to third order term, right? So e to the power a and e to the power b. Now, if you only consider the third order term, so all the other terms will get cancelled out. So let's consider only the third order term. So what is the third order term? So from the left hand side, I am writing as L3. It will be 1 by 3 factorial a cube, 1 by 2 factorial 1 factorial a square b. So I'm writing this from this Cauchy's product. So,
Uh,
so here I only want to consider k up to 3. So k equal to 3. So now my n will be 0, 1, 2, and 3, right? So I will have a cube, b cube, and all the other terms. So this will be your a square b and 1 by 1 factorial 2 factorial ab square by 3 factorial b cube. Okay. Now you just simplify these things. So it will be 1 by 6 a cube, 1 by 2 a square b, 1 by 2 ab square plus 1 by 6 b cube. So this is the left hand side. That was simple. Now your z is a plus b plus c2 that we have already proved. That is half of ab, half ab commutator and c3. Now, when you expand the right hand side, so you have e to the power z. So up to third order, that is 1 plus z, z square by 2 factorial, and z cube by 3 factorial. Up to this term, if you expand, so only the third order term, like R3, I'm just writing the third order term because all the other terms will get cancelled out. So from z from this z term, what is the third order term only left there? So from this z, the only third order term is c3. So from this z, you are only getting c3, right?
hmm.
And from this z square, so now what you have here? You have a plus b, that is your first order term. A and b both are first order. So the only way you can get from this z square term, so
A
if you,
square B and B square.
yes, like is no, like A C2, B C2, or C2A, C2B, these kind of terms only, right? Because
But you
they
want
will
third order, right?
only third order. So we are writing only the third order terms here. And all the other terms like C2 square, that is your fourth order, C3 square, that is your sixth order, or C2, C3, that is fifth order, those terms will not be there. So only terms will left, so that will be your half A plus B times C2 plus C2 times A plus B. And from Z cube, the only term, so if you take the cube, so if you take the cube only, if you can see that this term will survive. All the higher order terms, like in the R3, they won't be there.
But in 1 by 6 A plus B whole cube, if you expand it, you get higher order terms.
How? So this is a polynomial expansion. You get only up to third order A square B or B square A or B cube. They are only third order terms. What is the problem?
Oh, okay, got it. Sorry.
Okay, so your R3 is basically the sum of this, all the three terms. Now if you do L3 is equal to R3, and I should warn you that this is very cumbersome, and I have done once this. If you can do it, that is fine. But if you understand the logics, that is I think most like more than enough. So if you do L3 and R3, and if you put the value of C2 like this one, then you can actually get that your C3 is a uh, nested commutator like A comma B, and uh, this form. Actually you get it. This is a nested form. Then in the fourth order term, so there will be another nested. So A comma about A comma this term itself. So there will be third commutator. Like this it goes on. So
We have to
so
show L3 equals to R3.
yes, if you do L3 is equal to R3, then there you can actually extract that what will be your C3. All the terms will get cancelled out. Only this term will be there. You have to do it actually, but it is very long. I think it will take another 6 PowerPoint slides, I think, but it is very lengthy. So, but the idea goes like this. So actually, why I'm showing you all this, because in the couple cluster expansion, you get actually something like this fellow. In the couple, I'm just telling you, you don't have to worry about this. So there actually you can write this like this H and half HT, and this 1 by 3 factorial H HT. It goes like this. So this is called the Baker-Campbell-Hausdorff expansion. So that's why it is good to do all these
This
calculations
is
once.
there in this course, this expansion.
Uh, I think couple cluster is there, but this is called, yes. So you actually see this psi written as e to the power t is operating on psi Hartree. That part is there, I'm sure, but I don't know that this h psi is equal to e psi, whatever it will come out. But actually, the way it is solved is through this similarity transform Hamiltonian that I have told you. I'm not sure that whether it is being taught, but anyone who is interested to do this couple cluster in a advanced studies, they must have to go through this. There is, so actually that is the way people solve. So I think in a very few classes your couple cluster will be discussed. But yeah, if I get some time, I can take one class on this. Okay, so let's discuss the slides.
Do you have like problems on the last 2 weeks, like 6 and 7 basis set, then
So for
unrestricted
basis
hard
set,
fork,
for the basis set, the
and
only problem comes that is your
explainer.
counting your counting the basis functions or the what will the basis dimension. That is the only kind of problem you have. Or they can ask you like given a basis functions 6311G or kind of. So how we'll get the how many number of diffuse functions is there, this kind of problem. And for the as a many body perturbation of theory, uh, yes, there are some questions that came in the NET exam that I have seen in terms of many body perturbation theory that I'm planning to solve in the next class, uh, where does this the second order these equations I think already uh,
And also Ruthan equation and those.
Ruthan equation. As of now, I don't have any questions so far, but yeah, maybe if I get somewhere in any assignments or any questions I can solve. But actually, this is whatever I have in my experience, I have seen. Uh, Actually, this is a theory-based course, and if you see your assignment questions also, that is also very, I think, very straightforward to do it. Like if anyone has attended the classes and lectures, they have the notes, they can easily write down the expressions.
Actually, the assignment questions are easy. That's why I was telling. Like, do we
Yeah,
need to go through any books, exercises like Levine back exercises?
yeah, I haven't seen the Levine books, the questions there, but I was looking in the Zabo's book and I have solved some of the questions. But yes, there are scope of doing it, but mm so my plan is to actually give you more informations, like more information in the sense, whatever the plots or extra things that are there in some of the these David said lectures. So I wanted to discuss those, and so there are maybe 4 5 class left. So one class I'll do the this Hartree-Fock coding in Python. That is one goal, and another goal is to show you one. I think that will only be discussed. That is called the Weeks theorem. Uh, so that I'll discuss, and in that course, yes. So I have some questions in terms of the Hartree-Fock theory. Uh, in Hartree-Fock theory, where orbital rotations that I have discussed back then, that was solved. Uh, yes, I have one or two questions. So maybe
Maybe
we
you
can.
can discuss the Zabo question, one or two Zabo questions every class. Like,
Okay, okay. I'll try to, but I don't know whether. Yeah. Okay. So let's discuss this. Most of the things were discussed, but still some of the part might be interesting. So this is taken from the Michael Marshall slides. The first thing is as why we need even many body perturbation theory or Rayleigh-Schrödinger perturbation theory, molar pressure that we are actually discussing it. How Rayleigh-Schrödinger perturbation theory and molar pressure theory are same in the partitioning scheme, and what are the other. I'll just mention that what are the other perturbation theory scheme is there, and applications of many body perturbation theory and failures we'll discuss. So what we have been taught, that is Hartree-Fock, yes. Density functional theory we haven't discussed, so we'll not. So couple cluster theory, it will be discussed, and configuration interaction, I think it is briefly discussed. Right. So now why do we need the Hartree-Fock or many body partition theory? Now in the Hartree-Fock theory, it doesn't accommodate the dynamic electron correlation. Now, what is the term dynamic electron correlation mean? So actually, the correlations that it is actually very vaguely or broadly divided into static and dynamical correlation. Though their separation is not very clear in the
Your
literature.
voice is fluctuating.
Yes. Uh, So the electron correlation, that is broadly or vaguely divided into two parts, static and dynamical correlation. Now, what is dynamical correlation? Let me discuss first, then I'll talk about what is static correlation. So, in dynamic, you have this is your occupied orbitals. So, here all the levels are occupied, and here you have your virtual orbitals. Like now, this you take as your Hartree-Fock determinant, right? But you know that only one Slater determinant is not sufficient. So you have to take all the other Slater determinants to get the whatever that is the exact solution, that is the full sphere. So if you take the other determinants, for example, the single determinant or singly excited like this, there are other, and so here is one electron, and somewhere down the line there is other. So you are taking all the singles and doubles. If you take all the interactions, so what actually you are doing, you are actually taking care of the electron correlation. So initially the electron was here. Now because of the repulsion, the electron wants to tries to be separate away from each other. So the electron might go here, but we don't consider in this Hartree-Fock picture. So actually this, when you take all these determinants instead of on top of the Hartree-Fock, these actually cause the dynamical correlation. Now, let me tell you what is static correlation. The static correlation actually comes in the near degeneracy level. So let's say this is your uh, occupied level in the Hartree-Fock, and there is another level virtual that is very close to the HOMO. So if this is your HOMO and this is your LUMO, and if the energy gap is very low, so you can say that, let's say the name of this orbital is A and this is I. So here you have another other occupied orbital. So now you have considered this as your Hartree-Fock. But in another solution, as the energy of this LUMO and HOMO is very same, one can also construct. So if this is your A and this is your I, one can construct Hartree-Fock from these determinants also, and which will be very similar of energy, because these HOMO and LUMO are very same they have the same energy or near degeneracy. This is called the near degeneracy. So in terms of near degeneracy, even if your Hartree-Fock is not good, so they are actually one do multi MCSCF, multi-configuration self-consistent field. So there they actually take the linear combination of these two determinants, and this is called the static correlation. So instead of this one determinant in the Hartree-Fock, you are in your reference state, you are taking another configuration. This is called the static correlation. So the static correlation arises when there is a very near degeneracy problem, and in the dynamical correlations, so whatever the determinants that were not there in the Hartree-Fock or reference picture, you consider all those determinants. That is called the dynamical correlations. So in the Hartree-Fock doesn't account for the dynamical electron correlations, so we need to go beyond that So we need many body perturbation theory. And I think you have already seen that there you actually in the second order you get the um, um, you get the doubly excited determinants. So you actually considering the dynamical correlations. Is it clear the difference between static and dynamical correlation? Okay, so now we'll not discuss the density functional theory. Now, why we need the many body perturbation if we look the couple cluster, which is a superior method than many body perturbation theory. So the CCSD method, if you know the in one of my class I told you, for example, the single doubles, it is n to the power 6 scaling or n to the power 7 scaling. As the scaling is very high, you actually cannot go beyond medium-sized molecules or large molecules or very large basis set. So that is one of the
What does
limitation.
the scaling refer to here?
Hmm.
Scaling, like what here? I
So,
don't remember actually.
uh, so, so when I discuss the Hartree-Fock slides from this David Cyril, there they have mentioned that your Hartree-Fock is n to the power 4 scaling. Now your CCSD becomes n to the power 6 scaling. So actually, um, scaling means, let's say you have a, so how do I explain? So let me see. Okay, so in couple cluster single doubles, I'm talking about. So there you have some amplitudes. So you may not be aware of this, but just let me tell you that in matrix multiplications, like for example, AMN and B, let's say um, BNK, what it gives is it gives you the matrix element of the C MK. Like so, this is one kind of matrix multiplication where the tensor you are talking about, this T amplitude, this is not two-dimensional. This is four-dimensional. Okay, so it is IJAB, and again you have so the two electron integral ABCD. This is also four-dimensional thing. Now it does the matrix multiplication, and you get again four-dimensional quantity, that is IJCD. Now look at this term here. So what is the scaling here? So the scaling is, let's say your um, m goes from 1 to n, and your
Is the scalar?
sorry,
T here is a scalar or something?
yeah, t is a uh, it's a four-dimensional tensor. Yes, the every individual number like IJAB. So you can every number is a, scalar number, but it is a tensor. It's a four-dimensional tensor. So in the many-body perturbation theory, I think if
So the
you
antisymmetrized integral is a one-dimensional quantity. You're telling.
it's a four-dimensional tensor, like it's a four-dimensional matrix. You can say it is a
And the
four-dimensional.
integral term, like
Yes, like individual term is a number, like one
and
one.
the integral, like the in the Dirac notation, what you wrote, ABCD, that is a number. That's a scalar.
Yes, that is a number, but that is for a specific. So when you are writing A, B, C, D, right? So let's say you are saying that my A is 1, B is 0, C is 0, or D is 5. So at that particular ABCD index, it's a number, right? So A can vary from your 1 to n, and B can also vary from. So now you have to put all so what is the matrix? It's an array of number, right? So every A12 or A21, these are just numbers. But as a whole, A is a two-dimensional matrix. So your AB RS, so individual, so your A can go from 1 to n, B can go from 1 to n, right? So now when you store all this number, because you have four indexes, it's a four-dimensional tensor. So to pinpoint a particular number, you have to give at least four index. So that's why it's a four-dimensional tensor. Okay, so whether they have mentioned.
It's you're multiplying t with a tensor.
Yes,
Number t.
you can multiply two tensor. Like these are some kind of
That gives
matrix.
a tensor with the same dimension.
Yes, the same dimension we are getting here.
Actually, we have not done anything about tensors, so I'm saying
Yeah, yeah, that's fine. So that's what even I didn't want to discuss, but back then I had a slide. I don't remember the equation. So let me give you the simple example. You will understand from here what is a scaling. So just let's look at this two matrix multiplication. So to do this matrix multiplication, how many times you have to compute all the numbers? So let's say your m is goes from 1 to n, and n goes from 1 to so okay, so let's say your this goes from m goes from 1 to m, n goes from 1 to n, and your k goes from 1 to k, right? So to form this total C matrix, how many like how many times you have to do the calculations? So for every m, now there will be this number of n and there will be this number of k. So actually what you are doing here, the number of times you are doing the matrix multiplication is m
and q.
times n times k. So for each, so how do you do the, so for every m, so you run from 1 to m, and your n also goes from 1 to n, and k goes from 1 to k. So this is your number of times you do this multiplication. That is the scaling. Now if you look at this four-dimensional here, so you are forming a four-dimensional IJCD, right? So let's say all the indexes that is goes from n, like 1 to n. So you have I that is goes from 1 to n, your j goes from 1 to n. Now this AB, these are common. So here you have to only they will contract. So in the final index you can see there is no AB, just like this n. So you have to consider only once. So for A and B it will be NN, and again now you have CD. So this is n to the power 6. When you go to CCSDT, this is wrongly written. This has to be n to the power 8. If you go to CCSDTQ, that is n to the power 10. So you cannot actually do all the calculations. In my previous lecture, I have showed you um, with just 10 number of electrons and some number of bases. If you just see the number of determinants in the full CI and CISDT level, if you see, it actually goes to the billion with the simple 30 electrons in 30 orbitals or 20 orbitals. So you just forget about doing the full CI calculations for a big molecule or in a large basis set. You just forget about it. So that's why for the CCSD, yeah, that is true that the CCSD is more better than this many body perturbation theory, but the scaling actually kills. So that's why we need the many body perturbation. So it is actually giving you the motivation. Why do you need even the many body perturbation theory? So another thing is that Hartree-Fock is n to the power 4. That is fine, but we don't have the dynamic electron correlation. So for the dynamical electron correlation, let's go to the CCSD. But yes, it is n to the power 6, so we cannot go beyond medium-sized molecules. Now again, there is the configuration interaction. This full CI, you look at the scaling, this horrible term, n factorial, and n to the power 6. So these are very costly method. Now, the many body perturbation theory, it is n to the power 5 scaling, which is yes greater than um, this Hartree-Fock theory, but it actually can take care of short and long-range dynamical electron correlation. And that's why we want to study the many body perturbation theory. Now, quickly, I want to discuss whatever has been discussed so far. To let's say we have a total Hamiltonian for the anharmonic oscillator. That is your half kx square. So up to this is your simple harmonic oscillations, and this is the higher order term in terms of. So if you go beyond the simple harmonic oscillation, so yes, for the simple harmonic oscillations we know the exact result, but for this anharmonic oscillator, how can we use the result of this simple harmonic oscillation? That actually can be given by the perturbation theory. So this we are defining as my zeroth order Hamiltonian, and this as my perturbation, right? So for this system, I know the exact one, but this is when my lambda is equal to 1, I get back my exact Hamiltonian. Now the quick recap. So you just put h psi n, and in place of h you put zeroth order h0 and lambda v, and you can actually now your psi n is a dependent of the parameter lambda, and en also a parameter of lambda. Now you can do a Taylor series expansion around lambda 0 because you know the psi n and en 0 around this point. So that's why you are doing a Taylor series expansion around lambda is equal to 0. Okay, so this is a very well-known Taylor series expansion of psi n and en. So this is the whole form, and this is the the kth order perturbation in wave function, that is written in 1 by k factorial del k psi n del lambda k at lambda is equal to 0. So similarly, the enk is also written. So you can write the psi n as psi n 0, lambda psi n like first order, second order. Similarly, the en in the order wise expansion. Now you put back all these terms here. H0, your psi n, and your en, and again psi n, right? So left hand side and right hand side must be equal to for a given power of lambda. So let's collect all the order-wise term. So in the lambda 0, so zeroth order term, this is our well-known, this is the exactly solvable problem. So we are doing around this lambda is equal to 0, all the Taylor series expansion. And they have collected the terms for this lambda to the power 1. So you have 0 and 1. If you take the product, it will be lambda to the power 1. And again, this is 1 and 0. So in the left-hand side and right-hand side, the order has to be same. Similarly, this is the second order term. Now, yes, this is the kth order term they have simplified. So in the left-hand side, you have only two options. So A is 0 because your Hamiltonian is A0 and V. So to get the kth order, you will take the kth order perturbation in the wave function and k minus 1 order perturbation in the wave function, and you take all the summation where I is equal to 0 to k, and this I and ki, if you see, this give you k. So yes, then the zeroth order correction, if you left project, so in this equation, if you left project with psi and 0, you get this expansion. So this A0, when operate on this psi and 0, you get this En0, and En0 is the thing that we already know. And this is our reference. Now the first order correction. This is your first order equation. If you let project with 0, what you have here, so when this H0 operate on this, because H is Hermitian, so H0 can operate on here, that will give you En0, and because of the intermediate normalization, this psi n 0 and psi n 1, that will go to 0, and this term will survive, and this will again, because this is just a number, it will come out from here and it will be 0, and yes, and this will be 1 because psi n 0 and psi n 0, they are normalized. So you are left with this equation, the first order, and this is the second order equation, exactly the same way they have did. So in the intermediate normalization, what it is considered is that, so your psi you are writing in terms of psi 0, psi 1, dot. So the intermediate normalization is helpful in deriving some equation. It is nothing but is that your psi 0, that is 1, and psi 0 with any other, this is actually 0. So when k is not equal to 0. This is the intermediate normalization. So which makes it, when you take the full this side, it actually no longer remain 1. But if your calculations is getting simpler and you get the wave function, you can always renormalize it. So normalizing a wave function, it's not a big deal. So if your calculations are getting very simpler, so you can use that, and later when you get the wave function, you renormalize it. That is the goal. So actually here you will have many other terms like psi 1 1, psi 2 2. So if you expand this, this will be greater than or less than 1, but it is not equal to 1. So that's why it is called the intermediate normalization. But again, the near normalizing is not a big deal. Now this is the second order corrections. This is the kth order correction, the general rule. We'll quickly go through this. And this is the perturbed wave function. So the any kth order wave function, I don't know what is my kth order wave function, but I certainly know the zeroth order wave function. And as I know the zeroth order wave function, and they are complete in nature, the complete basis set, I can write the kth order wave function as a some linear combination of the zeroth order wave function. Right. Now, so this is your first order wave functions, and in place of this first order wave function, they have put a summation over mu, and this is your expansion coefficient, and this is your zeroth order wave function in terms of they have written. Then similarly, this psi n this is also replaced by the same expansion, right? Now, if you equal, so now if you let project with the zeroth order nth wave function, what you have, so this will be delta mu nu,
See,
delta mu mu. So only when your nu is mu, so like the here mu goes from 0 to infinity, right? Not equal to n. This is fine. Now when this mu will be new, only this term will survive, right? So again, this is fine. This is the only term that will also survive. And here also, this is delta nu mu. This will survive. And this is what you have here. You have
actually, in the
psi.
class, we have not yet written kth order wave function as coefficient times the ground state, zeroth order.
So in class, it is not discussed, right?
Not yet time.
Yes, but actually it will be discussed in there that way also. So you know so the thing is,
What is C actually?
it's just a coefficient that you have to determine. Okay, so to get the second order energy,
Okay.
you need the first order correction, but you don't know what is my first order correction. That you don't know. But I know my zeroth order wave function. So I can write any kth order correction in terms of my zeroth order energy because I know it, right? So the coefficient will vary depending on whatever the correction is. So I have to determine the coefficient, right? So that's what we are doing here. Okay, I thought that it is been done, but yeah, actually it will be done, and then I think it will be even clear. But let's go through this. So in place of this psi n first order, you have put this. Now when why this mu is equal to not equal to n, that we'll see from here. If your mu so here if your n is equal to mu, so then the denominator will blow up. So your mu has to be not equal to n, right? So
Hmm.
So now you in place of this psi n1, you put this expansion, right?
One.
Yes.
Uh, earlier on, why didn't we learn like writing the case order perturbation as in terms of a coefficient? Does it come only in like second order correction where we're trying to identify?
So in the first order correction, you don't need in the first order correction you need only the zeroth order term, and you already know it, so you don't have to bother about that. But in the second order, you need the higher order wave function, the corrections. Right. So for example, this kth order energy, you need the k minus 1 order wave function. So, and you don't know it. So how do you calculate it? So that will be done by showing you that how do you calculate the first order correction in the wave function.
And
And if you
one double molar placid perturbation is basically a modified version of Rayleigh-Schrodinger.
not modified version, I won't say it's a modified version. So molar placid perturbation theory is a Rayleigh-Schrodinger perturbation theory when so I think yes. So see this slide. So Rayleigh-Schrodinger perturbation theory doesn't restrict the H, H0 and V. The Rayleigh-Schrodinger perturbation theory is in general. So you just do the partitioning. So there is one. I'll just mention there is one another perturbation theory that is recently become very famous by the Martin Hadron group. That is called the Brillouin-Wigner perturbation theory. So that is also Rayleigh-Schrodinger perturbation theory, but the way they do the partitioning, that is different. So in molar placid, when you define your zeroth order as the summation of the Fock term, then actually your Rayleigh-Schrodinger theory is nothing but the molar placid perturbation theory. So it's just a nomenclature. I think Moeller and Placer
Okay.
did it, so that's why it is with their name. But Moeller-Placer perturbation theory essentially a form of Rayleigh-Schrodinger perturbation theory. So whatever is discussed in Rayleigh-Schrodinger perturbation theory, that is actually will go straight forward with the Moeller-Placer itself. Right. So your task was to generate. So what is my coefficient? And now if you do the left project with is new zero to other wave function, from here is a simple manipulation. You can get this is what you need actually, and you got it. So you place this here. So this is nothing but your C nu 1. And in terms of the zeroth order, you are expanding. Right. Now if you put back here, or here, so you got all the terms in terms of zeroth order, and you use the Slater rules, and you get the second order. That will actually do in the Muller preset in a very short. So yes, this is my zeroth order, and the first order correction, they put the this V, this is your V here. So they put it here and they did some calculations. I don't know why they have did it, but yes, you can calculate the first order correction in the anharmonic oscillator. That's what they have shown you. And in the similar way, you can calculate the second order of itself also. So yeah, and the Moeller-Placer perturbation theory. So the Moeller-Placer perturbation theory, the H0 is the summation of your Fock operator. So in this is the Fock operator, which is your the core, and this is the uh, this is actually your Coulomb minus exchange, the effective one electronic operator, your Fock operator, right? Now, whatever the left is actually your total Hamiltonian is this this is plus. And so whatever left is 0. This is your V, right? And again they have, so this is the peril of copy pasting. I think, yes, this would be correct. This is your I to N.
You said this is an effective one electron operator or this is a effective two electron operator? Summation of all the Fock.
This is,
Yeah.
so Fock is a effective one electron operator. Fock.
Because we integrate over all the second electrons. That's why.
Yes, you try to do it, but because of the presence of exchange operator, you cannot actually do it. The total integration. So there was this term, right? So integration chi j star 2 1 by r1 2 chi j 2. This is fine. That you can integrate out, right? But there was this term chi j star 2 1 by r1 2 chi j 1 d tau 2. So this in a back way you even I don't know how they do calculate this exchange integral, uh, but that's why it is called the effective one electron operator, because you are integrating over this second electron coefficient. But here it's not possible to do it because of this exchange operator.
Still we call it one electron.
Yes, that's why it is called effective one electronic operator. But this HI, this is a one electronic operator for sure. So Fock is a effective one electronic operator. Now you do this partitioning. This is a notation. And can you see this? Why they have written this psi I and this effective? So this is this part. This part they have written here.
Yes.
And why they have written is an integral. From where this is coming?
The first term is column and second is exchange. So like this IB, JB, and is a
So
column and
if psi,
IBBJ is
I,
exchange.
and j, they are different by one index. This is Slater rule 1, I
It's
guess.
like a type 2, yeah.
Yes. Type 2 or yes, type 2, yes. Like where actually your I and j, it differs by only one spin orbital. I don't know what it called, 2 or 1, 2, I don't know.
Not
2.
differ by one.
Yes. So this is a Slater type rule.
Here it is
And
not differing, I think.
yes, it is differing. So this actually says that the here the I from ith orbital the excitation is happening, and from here the z. So here the ith orbital is vacant, but here the zth orbital is vacant. So this differs by I and j. So that's why it is coming out to be like this.
So the one electron Hamiltonian term disappears because of that.
No, like they have only written this term. If they have written your the psi I, H,
Yeah, yeah.
psi j, they could have got Aj. But they are only writing this part. That is there, but they have
I was
written
not
on.
getting like here replace. How is the replacement happening? Like psi A R because these both are Slater determinants, psi A and psi J.
Yes, so for example, let's say, uh, right, so if this is something psi I A, psi J A, so it's kind of single excitation.
Oh, okay, I got it, got it. Yeah,
Is it fine? So here is vacant. Yes,
yeah,
the
yeah.
nomenclature is not. I will say that clearly they have written it, but yes,
Okay,
so they can only write only this kind of phenomenon is happening, right? There is a difference of one spin
okay.
orbital. Otherwise, you cannot write it. So now the molar placer, they have written it, and the E00, they have written that this is, we have discussed so many times, the summation of orbital energy is not the Hartree-Fock energy. And yes, they have written the total summation here. Yes. Now they have just used the molar placer perturbation theory's result. So they have put the side Hartree-Fock determinant here, Hartree-Fock determinant here, and V is here, right? Now what is V? The V was 1 by Rij minus that Hartree-Fock I term that was there. So actually this term,
Hmm. Hmm. Hmm.
this term, they have put it here. Now you know from the Slater rule, I think Slater rule type 1 here because they have the same wave functions, that is 1 by half summation over AB, AB, AB. And here
Hmm.
also the this one, because this is a one electronic operator, so it's a psi Hartree-Fock, sorry, new Hartree-Fock A. And so now this E0Z, this becomes, now if you just put the, so the form of the V Hartree-Fock, that is the Coulomb minus exchange. So now it will be this, right? If you explicitly form the Coulomb minus exchange, so what is this? This is actually Coulomb minus exchange, or J minus K. Now if you put it here, you will get a
Can you
Dirac Hartree-Fock.
once tell the how the first term is coming like this one by R?
This form.
Yeah.
So from the Slater rule, so in the Slater rule,
Oh,
whatever
got it.
whatever
But there
you
there's a one index missing in the second term. That's I was in doubt.
here.
Oh no, it's again in the carried in the next one. Okay.
So in the first term, like in the first line, they haven't expressed the this V Hartree-Fock. They have
Basically, they're
later.
saying just a factor of half.
Hmm, hmm. So, so whatever you have learned is that H psi 0. Right, now this H is a core Hamiltonian plus 1 by R2, R12. And they have only written this 1 by R12 term. That's why it is here. And this is also very simple. Now if you do the summation, E0, 0 and E0, 1. And what is this? This is your Hartree-Fock energy. So this actually, I think in the class, it will be shown that if you do the separation like the Fock and the term, and you, okay, so I have a zeroth order energy and I will only calculate the first order correction. You actually end up in the Hartree-Fock energy that you already have. So you have to have go beyond at least first order. So you have to calculate at least second order to get the correlation. So this is so when you add the zeroth order and first order correction, this is a very classic example, or it is asked many times that the you have to go beyond first order energy to get the correlation. So up to Hartree-Fock there is no correlation, right? And in the previous class, I have discussed that in Hartree-Fock, actually, many people wrongly says that it's a totally uncorrelated part, but actually it is not. There is a correlation between same spin orbital, but there is a no correlation between uh, whatever the spin that are the opposite spin. So you please go and check out that. For the Hartree-Fock, it is not totally uncorrelated. For the same spin, there is correlation in the Hartree-Fock. However, in the second order, this is your formula, and this is you already calculated from the molar placid, Rayleigh-Schrodinger perturbation, the psi1, and you put back this, and this is the famous second order molar placid equation, and you calculate this from here. Now, which terms will survive? Now, your mu goes from 0, not 0, because 0, like mu goes from 1 to like this, right? Now, if your excitation level is singles, now psi 0, B psi 0, you know from the Brillouin's theorem, it will be 0, that is fine. Now, the doubles, that is, now the higher order excitations, because of the triples and quadruples, there are spin orbitals which differs by more than 2. That's why it is 0. That is also Slater rule number 3. So only term that will survive, these are the doubles. And they have calculated the terms, right? Very simple. Again, they have, I think they have used the Slater type rule 2 here because it differs by ABRS. So only 2 orbital. So that is
So
ABRS.
why did you say only the doubles will survive? Like, I didn't understand.
Okay.
Doubles.
So this is your energy expressions. Okay. So now your mu can goes from 1 to and all the, so actually your zeroth order is what? Zeroth order is all the Slater determinants, right? So there will be singles, doubles, triples and all. Now let's consider when your mu, these mu are only singles, right? So if you put the singles here, so because of the Brillouin's theorem, this psi 0 V and psi AR, that is 0. You know from the Brillouin's theorem. Now talk about the triples. Now if you put the triples here, so now in the triples, what does that mean? You are exciting 3 electrons from the reference. So now you have a difference from the left hand side and the right hand side Slater determinant which is greater than 2, the spin orbital difference. So from the Slater rule, again this is 0, so any higher order term will not survive, but only the doubles will survive because this term is ABRS from the Slater rule. Is it clear?
Yeah.
Okay. Now there is a denominator. I think is it fine that why they have written like this E00 minus E mu 0 as this? Is it clear to you? So when this A0 operate on this psi ABRS, so only difference is that from RS orbital, from RS occupied orbital, the two electrons are sitting now in AB. So only the difference will be there, that is whatever the in the zero state, so all the electrons was there in the RS orbital itself, but now the two electrons are in sitting in AB. So only A and B, these two electrons energy will be summed up and other two energies will be different. And that's why you get only the difference, that is EA plus EB minus ER minus ES, like epsilon, sorry. So this is a famous MP2 energy. And you can see the above term is positive. However, the below term, this is your virtual, epsilon A and epsilon B your virtual, right? And so and you know that the uh, so here E00 and E mu 0, so this is your excited state energies and this is your ground state energy and this is always greater than this ground state energy. So your the denominator is negative and the numerator is positive. So the MP2 actually gives you negative energy. And this is the interaction energy for the, so one example they have shown you for the interaction energy of AR2. So what happens is that AR2, it's not a molecule. There is a dispersion interaction, or you can say induced dipole-dipole interaction. So there Hartree-Fock actually fails miserably because for the van der Waals interaction, it is a total electron correlation phenomena. So there you need to do some electron correlations. So there is here the CCSD parenthesis T is the best one one can have, and then the CCSD is better and MP2. So near the equilibrium region, you can say there is a difference between kilocal. So it's a kilocal per mole energy difference. So yes, so you have to compromise between two. But yes, MP2 is fine at least for the interaction energy. But Hartree-Fock energy fails miserably for this. Now again, this is the H2 bond breaking system. So if you see the only this region near the equilibrium. So what happens is that when you stretch the bond too much, actually the near degeneracy comes. So then your static correlations become very important. And there your MP2 or the molar placet may fail miserably. But in the equilibrium, this is fine. So that's what it is given. Then you have this MPN series. So you can see a oscillatory behavior here, right? So now it almost converges as 6 or 7 or 5, you can say, right? It's at equilibrium distance. Now it's a 2.5 times equilibrium distance. Now you can see even if with 40, 50 MP like molar placet, it doesn't converge. It's a oscillatory behavior. Yes, so there are some drawbacks of molar placet perturbation theory. Okay, so um, maybe in the next class I'll show an example how to do a molar placet calculations in the Orca. It will take just another 5-10 minutes, and we'll discuss some assignment problem if we have, and one of the classes will show that how to code Hartree-Fock. Okay, thank you.